Hey everyone, and welcome back to the channel. Today, we're diving deep into one of the most mind-bending, universe-altering ideas ever conceived by a single human brain, Einstein's theory of relativity. But we're not just going to talk about E equals mc squared. We're going on a journey through time to uncover the story behind the theory. How did a young, unknown patent clerk in Switzerland completely rewrite our understanding of space, time, and gravity? It's a story of genius, rivalry, and a revolution that's still shaping our world today. So buckle up, because things are about to get weird. To really get this story, we have to travel back to the late 19th century. Physics was feeling pretty pleased with itself. Isaac Newton's laws of motion and gravity had reigned supreme for over 200 years. They could predict the orbits of planets, the arc of a cannonball. Everything seemed to fit perfectly. It was like a beautifully crafted clockwork universe. But there were a few pesky little cracks starting to show in this perfect picture. The biggest problem was light. Scottish physicist named James Clerk Maxwell had come up with a brilliant set of equations that described electricity. Magnetism and light is all being part of the same thing, electromagnetism. His equations predicted that the speed of light in a vacuum is a constant, about 300,000 kilometers per second. Now, this was a huge problem. According to Newton and our everyday intuition, speeds should add up. If you on a train moving at 100 kilometers per hour and you throw a ball forward at 20 kilometers per hour, someone on the ground would see the ball moving at 120. Simple, right? But Maxwell's equation said that if you on that same train and you shine a flashlight, the light beam moves away from you at the speed of light, and the person on the ground also sees it moving at the exact same speed of light. Not the speed of light plus the speed of the train. How could this be possible? It defied all common sense. This was the puzzle that kept physicists up at night. Enter Albert Einstein. In 1905, while working as a patent examiner in Bern, Switzerland, he had what he called his annus mirabilis, or miracle year. He published 4 groundbreaking papers. One of them, on the electrodynamics of moving bodies, introduced the world to the special theory of relativity. Einstein took a bold leap. Instead of trying to fix Maxwell's equations, he decided that the laws of physics, including the speed of light, must be the same for everyone, no matter how they are moving. To make this work, he had to throw out our old, comfortable ideas about space and time. He proposed that space and time are not absolute and unchanging. Instead, they are relative. They can stretch and shrink depending on your motion. This leads to some truly bizarre consequences. One is time dilation. The faster you move through space, the slower you move through time. It's not a feeling, it's a physical reality. If you flew in a spaceship near the speed of light and then returned to Earth, you would have aged less than the people you left behind. Another consequence is length contraction. Objects moving at high speeds actually shrink in the direction of their motion, as seen by a stationary observer. And then came the most famous equation in all of science, E equals mc, this little equation. A direct consequence of special relativity revealed a fundamental relationship between mass and energy. It says that mass is a highly concentrated form of energy. A tiny amount of mass can be converted into a tremendous amount of energy, and vice versa. This principle is the basis for nuclear power and, tragically, nuclear weapons. It fundamentally changed our understanding of the universe's energy budget. Special relativity was a masterpiece, but Einstein knew it was incomplete. It only dealt with constant uniform motion. What about acceleration? And more importantly, what about gravity? This is where the story gets even more interesting. Einstein spent the next 10 years grappling with this problem. He called this period the most intense intellectual struggle of his life. He was trying to figure out how to incorporate gravity into his new framework. His big aha moment, what he called his happiest thought, came when he imagined a person falling from a roof. For that brief moment, the falling person feels no gravity, they're weightless. Einstein realized that the effects of acceleration and the effects of gravity are indistinguishable. This is called the equivalence principle. If you were in a windowless elevator in deep space, accelerating upwards, the feeling would be identical to standing still in an elevator on Earth under the pull of gravity. This insight was the key. Einstein proposed that gravity is not a force pulling objects together, as Newton had described. Instead, Gravity is a consequence of the curvature of spacetime itself. Think of spacetime as a giant, flexible rubber sheet. Massive objects like the sun create a deep curve or a dent in this sheet. Planets like Earth aren't being pulled by the sun. They are simply following the straightest possible path through this curved spacetime. It's like a marble rolling around the edge of a funnel. It's not being pulled to the center. It's just following the curve. This revolutionary new idea was the General Theory of Relativity, which he published in 1915. General Relativity made some astonishing predictions. One was that gravity could bend light. Since light travels through spacetime, if spacetime is curved by a massive object, the path of the light must also be curved. This was a radical idea. At the time, there was no way to prove it. But an opportunity was on the horizon. A total solar eclipse in 1919. An English astronomer named Arthur Eddington led an expedition to observe the eclipse. The plan was to photograph the stars near the sun. During the eclipse, the sun's light would be blocked, allowing them to see the stars. If Einstein was right, the gravity of the massive sun should bend the light from those distant stars as it passed by. This would make the stars appear to be in a slightly different position than they actually were. The expedition was a success. Eddington's measurements confirmed that the starlight was indeed deflected by the amount Einstein's theory predicted. When the results were announced, it was a worldwide media sensation. Headlines screamed, "Revolution in science, new theory of the universe, Newtonian ideas overthrown." Albert Einstein, the former patent clerk, became an overnight global celebrity. It was the ultimate validation of a decade of relentless intellectual effort. But the story doesn't end there. Also predicted other strange phenomena. It predicted gravitational time dilation, meaning that time runs slower in stronger gravitational fields. Clocks at sea level tick ever so slightly slower than clocks on a mountaintop. This isn't just theory. It's a measurable effect that our GPS satellites have to account for every single day. Without correcting for relativistic effects, your GPS would be off by several kilometers within a single day. The theory also predicted the existence of gravitational waves ripples in the fabric of spacetime, created by massive accelerating objects like two black holes colliding. Einstein himself was unsure if they would ever be detected. For a century, they remained a purely theoretical prediction. Then, in 2015, exactly 100 years after Einstein published his theory, the LIGO experiment made the first direct detection of gravitational waves from two merging black holes over 1 billion light-years away. It was a monumental achievement that opened up a whole new way to observe the universe and once again proved Einstein right in the most spectacular way. From a puzzle about the speed of light to a complete reimagining of the cosmos. The history of relativity is a testament to the power of human curiosity and imagination. It shows us that reality is often far stranger and more wonderful than we can possibly imagine. Einstein's theories not only gave us a new understanding of gravity, black holes, and the Big Bang, but they also continue to be an essential tool for astronomers and physicists exploring the deepest mysteries of the universe. What started as a thought experiment in the mind of one man has truly become our guide to the cosmos. Thank you so much for joining me on this journey through the history of relativity. I hope you found it as fascinating as I do. If you enjoyed this video, please give it a thumbs up and consider subscribing for more deep dives into the wonders of science. And let me know in the comments what's the most mind-blowing part of relativity for you. Thanks for watching, and I'll see you in the next one.